Hello, I think it's recording now. Testing, testing, 1, 2, 3. Testing, testing, 1, 2, 3. You can hear me? Let me know. Just kidding. Okay, yeah, well, welcome back, everybody. Like I kind of said, in in class, I will be recording kind of a small video just to kind of finish up some of the theorems from the diagonalization section. A lot of the stuff there is things that we've kind of like talked about, but maybe haven't written out explicitly. And so I just want to use this space to kind of write it down explicitly. But first, some quick announcements. Many of them very usual for you, I would imagine. Homework 10 is due Saturday, May 2nd by 10 p.m. on Canvas. There is no class this upcoming, Monday, May 4th, or my usual office hours at that time. However, if you email me ASAP and let me know that you would be wanting to come to an office hours on Monday, May 4th at 10 a.m., then I will be there at 10 a.m. To take any extra questions. But you just email me in advance, otherwise I won't go. Um, if you fill out an evaluation, you get a third dropped homework. So please take advantage of this. Dropped homeworks are really useful. And this is all in preparation, of course, for the final exam, which is Friday, May 8th, not Monday. It's Friday, May 8th from 12 p.m. to 2 p.m. It'll only be 75 minutes long. This is the kind of scheduled time that they have for us. It'll be in the usual classroom, okay? Keep in mind, please show up. If you don't come, you are automatically failed the class. All right. Armed with that, I will go ahead and start with some examples from diagonalization just to kind of get things started. So let A be this matrix. And diagonalize A if possible. So of course, diagonalize means find lots of so diagonalize means make A look like a diagonal matrix. And how can you make A look like a diagonal matrix, at least according to the theory developed in the class? You can make A look like a diagonal matrix if you have enough eigenvalues. So this is kind of a long-winded way of saying find all the eigen stuff, every last piece you can think of. Find the eigen stuff. All right, so step one, of course, will be to find the eigenvalues. Find the eigenvalues. All right, and so as many of you guys know, this means that I have to consider the determinant of A minus lambda I. I have A up there, and so I'm just going to kind of write down, well, as a determinant. So I'm going to write down the non-diagonal entries of A, which are these. And now for the diagonal entries, I'm subtracting lambda I from them, so it'll be 2 minus lambda, 2 minus lambda, and 1 minus lambda. All right, and this is a determinant, and so I know how to take determinants. I'll take a determinant maybe along this this first row here. So I guess it will be 2 minus lambda times the determinant of 2 minus lambda, 1 minus lambda. Let me make some space. 1 minus lambda, 1 and 0. And this is a diagonal. The smaller minor here is a diagonal matrix. So I'm able to take its determinant just by looking at the diagonal entries. So that'll give me a 2 minus lambda again and a 1 minus lambda. And I can simplify this ever so slightly. This is 2 minus lambda squared, 1 minus lambda. And so that is to say, I know what my eigenvalues are. So my eigenvalues are lambda is equal to 1 with multiplicity 1. Lambda is equal to 2 with multiplicity 2, because it appears twice in this polynomial. All right, now that we have the eigenvalues, we can go on to step 2, which is find the eigenvectors. Okay, and so how do you find the eigenvectors? You have to find them for each eigenvalue, and so I'll just start with lambda is equal to 1, and then shortly thereafter, I'll go to lambda is equal to 2. So for lambda is equal to 1, eigenvectors of A corresponding let's write it like that, to lambda is equal to 2 can be found by computing the null space of A minus 1, 1i. So that is to say I have to look at an augmented matrix, all right? And so I know what A is, and so I can compute what A minus I is, and that, I'll leave it as an exercise to confirm that the off-diagonal entries are going to be the same as they were before. I'm only changing the diagonal entries, right? And now over here, previously I had a 2, previously here I had a 2, previously here I had a 1. So if I subtract 1 from all of these, as I do with the identity matrix, then this is going to go ahead and be a 0, a 1, and a 1. And I should probably augment 0, right? Because to remind myself, not that it does anything, this last column here, but it reminds me that I'm looking for kind of a free variables. I'm looking for a null space. All right. And so it looks like I can add the first row to the third row, and this will give me a row of zeros as I anticipate. I can grab the first row and subtract and then put a minus sign there and then add it to the second row, and that'll give me this. And so I am in a row echelon form. So here I have a pivot, here I have a pivot, which means everything that's not a pivot is automatically free. So x3 is a free variable. You have a name, so we give it a name. We call it t. And now I'm able to write the general solution, x, as x1, x2, x3. X3 was t. X1 you can see is going to be 0, and x2 is going to be negative t. I can take out the t part, 0, negative 1, 1. And so this tells me that the set 0, negative 1, 1 is an eigenvector for lambda is equal to 1. All right, so I'm kind of halfway there, let's say. Now I have to do the exact same thing, but for the eigenvalue, right? Maybe kind of what this is kind of morally shown is that you don't need to write this part, so maybe I'll put it in brackets, but I want to remind people of this terminology. So the eigenspace of lambda is equal to 1 is, by definition, the null space of A minus I, because it's lambda is equal to 1, times the identity. And by the above, it looks like I can just write this down as an explicit span of this vector. And so this is going to be some kind of one-dimensional eigenspace corresponding to this eigenvalue. All right. And so if I wanted to, I could say something like, so 0, negative 1, 1. Again, this is not something you're expected to write. I just wanted you to kind of see this. So this set right here is a basis for the eigenspace of lambda is equal to 1. All right, but now that I finished up the lambda is equal to 1 stuff, I can go over to the lambda is equal to 2 stuff. So lambda is equal to 2 stuff. All right, and that means I have to consider, the null space of A minus 2i. All right, and so I will jump straight to the calculation. So I can write down what A is. I remember the entries of A, right? So the non-diagonal entries of A are going to be 1, negative 1, 0, 0, 0, 1. All right, and now the actual diagonal entries are 2, 2, and 1. So when I subtract 2 from this, I get 0. When I subtract 2 from this, I get 0. And when I subtract 2 from this, I get negative 1. It's probably a good idea to augment the 0 solution. And now I can actually compute this null space, right? It looks like right away I can just add the second row to the third row, and I will get 0, 0, 0, 1, 0, 1, 0, 0, 0, and then 0, 0, 0. Maybe it makes sense for me to move the 1, 0, 1 to the very top, just for kind of posterity. And this is the null space, right? So as before, I can count my pivots. My pivots are over here, which means I have everything else is a free variable. So that means x2 is a free variable and x3 is a free variable. I'll call x2, let's say t, and I'll call x3, let's say s. And, I can now kind of solve for the solution of this. So this tells me that the general solution, x, is going to be x1, x2, x3. X3 you told me was S, X2 you told me was T, and then X1 is going to be negative S, I think. Yeah, negative S. All right, I separate this into the S parts. How many S parts do I have? I have negative 1, 0, 1. How many T parts do I have? I have apparently 0, 1, 0. So now I want to kind of notice something. So this tells me, for example, so the eigenspace of lambda is equal to 2, which is given by the null space of A minus 2I. This thing right here is two-dimensional. All right, I think this might be the first time that we've seen this, right? So I have an eigenvalue. This eigenvalue notably had multiplicity 2. So this 2 corresponds, or the fact that this could possibly be 2 corresponds to the fact that I had multiplicity 2. All right? And so, how you say? And so, like, this might be having a chance of being diagonalizable because kind of just thinking about it, I got one eigenvector over here from lambda is equal to 1. And now I just showed that the eigenspace over here is two-dimensional, so I end up with 3 eigenvectors. All right? And so, yeah, so I end up with the eigenspace that's two-dimensional. And a basis is just given by grabbing these two vectors. Okay? And now what I'm able to do is I'm able to go to step 3, construct P, and check it is invertible. All right, so to check P is invertible, I will, well, I have to construct P, I should say, and then check it's invertible. All right, so what's P going to be? P is going to be the matrix of eigenvectors. All right. And so I solved for lambda is equal to 1. I had one eigenvector that was given by 0, negative 1, 1. And then for lambda is equal to 2, I had two eigenvectors, namely the ones above here. Maybe I'll write this one first, 0, 1, 0, and then negative 1, 0, 1. The order of these two doesn't really matter because they're part of the same eigenspace. And now I can check that it's invertible by just computing a determinant. So notice, maybe I should say one thing. In the past, some of our examples, this is for lambda is equal to 1, and this right here is for lambda is equal to 2. These are the eigenvectors. In the past, I was able to easily write down that P is invertible because the eigenvectors corresponded to different the eigenvectors corresponded to different eigenspaces. But I can't make that argument anymore. For example, over here, these guys right here are linearly independent, but I can't say that these three are linearly independent automatically. But I can easily check that it's going to be invertible by just computing a determinant. So the determinant of P is going to be 0, negative 1, 1, 0, 1, 0, negative 1, 0, 1. I can do a cofactor expansion along the top. And this will give me plus minus plus, so it's going to give me a negative 1 times negative 1, 1, 1, 0. And then this determinant is going to be, well, negative 1 times 0, 0, minus 1 times 1 is a minus 1, so it's going to be a 1. Notably, this is not 0, so P is invertible. So this is what sometimes what students will kind of forget to do. They find P, but they don't actually check it's invertible. Please do make sure that it's invertible. Otherwise, this is all for nothing. All right, and now step 4, construct D from the eigenvalues. All right, so D is going to correspond to, where its eigenvalues 1, 2, and 2. And notice that I'm keeping, the order of D in the same order that I put that I put P. Right, so P, I put the lambda is equal to 1 eigenvectors first, and then the lambda is equal to 2 eigenvectors. So I'm forced to put the lambda is equal to 1 eigenvector first, and then that is to say lambda is equal to 1 first, and then I put lambda is equal to 2 and lambda is equal to 2 in the second and third diagonal entry. Okay, and now by the theory, if you want, we know that A is of the form P D P inverse. Okay, but and so you're done with this question. So we're done. All right, so A is diagonalizable. You're able to kind of check this again relatively quickly by kind of doing the computation, but I want to kind of go through this. You're done here. You don't this checking stuff that I'm doing, you don't have to do. I just want to help you guys with why this process works. Why are we done here? All right, so note A is equal to P D P inverse is going to happen if and only if A P is equal to PD. So it amounts to checking this computation, to grabbing A and P, multiplying them, grabbing P and D and multiplying them. But I can check this in the following other way, right? I can grab AP and then write down what P is. P was, consisted of three eigenvectors. The eigenvector corresponding to 1, and then two eigenvectors corresponding to 2, right? So maybe it's worth writing that down. So this goes to lambda is equal to 1, and this right here goes for lambda is equal to 2. All right. And now what I can do to compute this is I can, just construct a matrix that looks at A0, -1, 1, and then A0, 1, 0, and then A, -1, 0, 1. But I constructed these vectors, this P, exactly because they're eigenvectors. So what does it mean for this thing to be an eigenvector with lambda is equal to 1? It means when I look at A times this vector, I better get just 1 times this vector, or just this vector. Okay, maybe I'll leave it like that. And now over here, what am I supposed to get? Well, this is the eigenvector corresponding to lambda is equal to 2. So when I grab A and I hit it against the eigenvector corresponding to lambda is equal to 2, I better get 2 times the eigenvector, 0, 2, 0. And similarly over here, this is going to be the eigenvector corresponding to lambda is equal to 2. So when I grab A and I hit it on this vector, I know I made it this way basically. You can check the computation if you want, but I know I'm going to get -2, 0, 2. Okay? But now what is this? This is the same thing as the matrix that I get by doing this vector first, and then 2 times this vector first. Sorry, this vector, and then 2 times this vector. But I can write this multiplication in a slightly different way, right? I'm able to write this multiplication by, this is basically grabbing this first vector with weight 1, the second vector with weight 2, this third vector with weight 3. All right, and this is just a matrix multiplication of what? This is a matrix multiplication of P, which is 0, -1, 0, 0, 1, 0, -1, 0, 0, times the vector 1, 2, times the matrix 1, 2, 2. Okay, and so I'll leave this as a kind of exercise for you guys to confirm, but this is exactly PD. So this is why you never have to check this, because the fact that you know what eigen stuff means you don't have to check this. The theory tells you that AP is equal to PD, and as such, A is diagonalizable, assuming that the matrix P is invertible. So the hard part is computing the eigenvalues and then computing the eigenvectors, and then finally checking that P is invertible, where P is the matrix of eigenvectors. All right, and so here's a theorem that we've kind of been brushing around a lot. It's the diagonalization theorem. That morally is kind of what we've been saying. So an n by n matrix, A, for example, a 5 by 5, is diagonalizable if and only if A has n linearly independent eigenvectors. That is to say, I have so many eigenvectors that I can form a basis of Rn, right? So this is what it means to have enough eigenvectors, okay? Yeah. So this is kind of our main result. All right, so let's see, this is kind of what I mean by enough eigenvectors. So let's keep doing some examples. I think the examples are kind of where the money is. And before I do the example, let me just double check something really quick that I want to make sure I didn't do this example yet, basically. Um, in a previous class. Oh, whoops. Wrong notes. Yeah, we're already, according to my clock, 20 minutes in. It gives you a sense of kind of just how time intensive some of the eigen stuff is, right? You have to compute a lot. Each kind of step, I hope, is kind of reasonable for you. I'm optimistic that it's reasonable for you, but it's a lot of little steps. So it's kind of, it's hard, I think. I don't think it's an obvious thing. Okay, yeah, I don't believe we did this example, which is good. Good. All right, so let's keep going. So let A be 2, 0, 0, 6, 1, 0, 2, 3, and 2. So I don't believe we've done this example, at least according to my notes. Yeah, I think we're good. All right, so let's go ahead and do this example together. So let A be this, diagonalize if possible. All right, so we go through the entire process, but we notice some things, right? We're not just robots and just kind of going through the motions. We're able to kind of look at these things. So note at what kind of matrix A is. Yeah, so A is a triangular matrix. And this is awesome because it implies that the eigenvalues are easy to compute. The eigenvalues are the entries on the diagonal. All right, so in particular, lambda is equal to 2, 6, and 1, 2, and 6, all with multiplicity 1, multiplicity 1, multiplicity 1. All right. And now, you may like to think that you have to kind of go through this runaround of now finding the eigenvectors, but we don't have to, because this guy right here is going to give me the fact that lambda is equal to 1 means that it has an eigenvector. Let's call it maybe v sub 1. The fact that I have this eigenvalue means there's an eigenvector v sub 2, and the fact that 6 is an eigenvalue means it has an eigenvector v sub 6, let's say. Um, so like by virtue of me having an eigenvalue, I'm forced to have an eigenvector. I'm forced to, because that's what it means to be an eigenvalue, is that I have an eigenvector. All right. And so this tells me that I have v1, v2, and v6 eigenvectors, and now I need to check that they're linearly independent. I need to basically check that if I form a matrix P with 3 of its eigenvectors, this is going to be linearly independent. But what can you tell me about these 3 eigenvectors that we haven't picked out? We haven't written them explicitly, but what can you still tell me about these eigenvectors, even though we have no idea what they are? We just know that they exist. Yeah, you can tell me that they're coming from different eigenvalues. All eigenvectors are coming from different eigenvalues. So since they all come from distinct eigenvalues, they are linearly independent. And so A is diagonalizable. This notably didn't happen in our last example, right? In our last example for 3 by 3, we had two eigenvalues. Namely, we had, remember, a lambda equals 1 and a lambda is equal to 2 in the previous example. And in the lambda is equal to 2 case, um, we had to kind of check, we had to check in this case by hand whether the matrix of eigenvectors was invertible or not. In this case, by virtue of them coming from different eigenvalues, lambda is equal to 1, lambda is equal to 2, and lambda is equal to 6, I get to just use a theorem to say that they're all going to be linearly independent, and as such, A is diagonalizable. Okay? So that's nice. It's sometimes nice when the theory kind of takes over and you don't have to do any thinking. So diagonalize, just keep it going. A given by 2, 4, 6, 2, 2, 4, if possible. All right, so up to now, you may be thinking that every single matrix is diagonalizable, right? Every single time that we've had a matrix, we found its eigenvalues, and the eigenvalues have either always supplied all of the eigenvectors. All right, so let's take a look at this example and see if that's a general trend. All right, so since notice that I have to find the eigenvectors, right? So maybe I'll write that. Okay, step 1. Find the eigenvalues. Well, what kind of matrix is this, guys? Yeah, it's a triangular matrix. So since A is triangular, then the eigenvalues are lambda is equal to 2 and 4. Here with multiplicity 2, and here with multiplicity 1. Because it appears once, right? This 4 appears once, this 2 appears twice. And I know these are the eigenvalues. In general, right, the diagonal of a matrix is not going to give you the eigenvalues. But I know here it's going to give me the eigenvalues because it's a triangular matrix. Okay? All right, and so now as before, I can just find the eigenvalues and eigenvectors of all of this. All right, so maybe I'll start with step 2. Eigenvectors. All right, I'll start with lambda is equal to 4 just because. All right, so for lambda is equal to 4, I need to consider the null space of A minus 4i. All right, and so what that means is I need to grab A, and I'll write down A here for everyone's memory. I need to write down A. All right, and now I need to subtract 4 from the diagonals. I need to subtract 4 from the diagonals. When I subtract 4 here, I get 0. When I subtract 4 here, I'm going to get a negative 2. And when I subtract 4 here, I also get a negative 2. All right, and since I'm looking for null space, I want to join the 0 vector to this. All right, and now we can start to compute. I can see automatically with no effort at all, I ended up with a row of all zeros. So that's very convenient. And I can see that if I grab the second row, multiply it times 2, and add it to the first row, I can get a lot of zeros there too. So this is going to go ahead and be negative 2, 2, 0, 0. 0 by construction, and then I guess 10. Yeah, and now I can simplify this a little bit by dividing this row by negative 2. So I'll get a 1 here, 0 here, negative 5, 0, 0, 0, 0, 1, and negative 1, 0, 0, 0. Okay, and so now I'm kind of done, right? So as before, I have my pivot here, I have my pivot here, which means everything that remains here is going to be my free variable. And now using this, I'm able to write down a general solution. X is going to be given by x1, x2, x3. x3 you told me was t. X1 is going to be, I guess, 5t. And then x2, I guess, is going to be t. I can take out the t part. This is going to be 5, 1, 1. And so this tells me that the eigenspace for lambda is equal to 4 is, well, this is just going to be the null space of A minus 4i. And by the above, this is going to be spanned by a single vector, 5, 1, 1, right? And so it's a basis. So a basis is, for example, the vector 5, 1, 1, if you want. Okay? So that's what a basis for this eigenspace is. All right, and so now I'm going to do this for lambda is equal to 2. Lambda is equal to 2. All right, so as before, now I have to consider null space of A minus 2I. All right, and so I know what A is, so I'll write down A kind of for posterity. It's 2, 2, 4, 2, 4, 6, 0, 0, 0, 0. All right, and so now when I grab this A and I subtract 2 from it, this is going to destroy this, leave a 2 here, and then I should probably augment the 0 matrix to remind myself that I'm looking for a null space, to remind myself that I'm looking for free variables. All right, and now I can do this one relatively quickly. This is going to be maybe I'll just start off with this one, 0, 0, 2, 0, 0, 0. I'm going to grab this second row, destroy the third row, grab the second row, destroy the 6 in the first row, and then I end up with a 4, 0, 0. All right, and then I can make some 1s out of this. It's going to be 0, 1, 0, 0, 0, 1, 0, 0, 0. Row of all zeros, exactly as I expected, because I'm looking for an eigenspace. All right, and so now kind of the $1,000,000 question for you guys is, can you guys recognize what the pivots are here? I think this is slightly a little bit different than what you guys are used to seeing. I hope everybody can see that this right here is a pivot, this right here is a pivot, so x2 and x3 are basic. And then that means that x1 is free. And so we give it a name, and we just call it t. And when I call this t, then now I can write down the general solution. x1 is going to be, this is t by construction. x2, according to this equation, is going to be 0, and x3, according to this equation, is going to be 0 as well. So this is just t1, 0, 0. Let me go ahead and clean this up. And so this tells me that the null space of A minus 2I is just spanned by this single vector, 1, 0, 0. So recall that lambda is equal to 2 had multiplicity 2. But in this case, it has a one-dimensional eigenspace. All right. So now if I wanted to diagonalize this, then I have to make, P and D. So step 3, construct P and D out of the eigenvalues. So for example, if I let D be the matrix of eigenvalues, well, it has 2 with multiplicity 2, and then 4 with multiplicity 1. So that could be, that's what my D would have to look like, basically. P now has to come from eigenvectors of 2. All right, so what are the eigenvectors of lambda is equal to 2? They're these guys right here. Anything inside of this span. All right, so I'm going to grab 2 of the vectors from this span right here. For example, I could grab 1, 0, 0. And maybe I want to grab 1, 0, 0 again, or I could grab 2, 0, 0 if you want. It won't change anything. And then last but not least, I grab the eigenvector corresponding to lambda is equal to 4, which earlier we showed was 5, 1, 1. All right, but now we have to check if P is invertible. Well, what can I observe about P? Well, P has 2 linearly dependent columns. This column right here and this column right here. And actually, for any choice of this column right here, I have to grab an eigenvector for lambda is equal to 2. And so they're all going to be some multiple of 1, 0. So no matter what I chose for this middle column, I'm always going to end up with 2 linearly dependent columns. And so in particular, P has 2 linearly dependent columns, implies P is not invertible, which implies A is not diagonalizable. All right. So the issue with this one, maybe I can write it down here, is like, note the eigenspace for lambda was equal to 2 is one-dimensional. It was only one-dimensional, right? It was spanned by 1, 0, 0. But lambda is equal to 2 had 2 as the multiplicity. So the kind of issue, the reason why I can explain the failure of diagonalizability for this A is that I didn't have enough eigenvectors. And the reason why I didn't have enough eigenvectors is because the dimension of the eigenspace did not match the multiplicity of the eigenvalue, right? The dimension of the eigenspace was 1, and the multiplicity of the eigenvalue was 2. And so that's the reason why I can explain the failure of diagonalization in this case. All right. And so, I want to give you guys some criterion, let's say, to be able to see whether something is diagonalizable, namely a way that you can easily see that you have diagonalization is possible for a matrix. So if I grab A inside of NN, so it's an n by n matrix, has n distinct um, eigenvalues, implies that A is diagonalizable. All right. So this is what we saw earlier, right? We saw this in a specific setting, example, or, old example. We saw this in the matrix A is equal to 2, 0, 0, 6, 0, 2, 3, 2, 1. This is one that we solved earlier. We saw in this case lambda was given by 1, 2, and 6, all with multiplicity 1. All with multiplicity 1. And so now the way we argued that this was diagonalizable was we showed that whatever eigenvectors corresponded to the different eigenvalues had to be linearly independent from the other ones by virtue of them coming from different eigenvalues. But now I can just use this theorem to kind of avoid that extra sentence, basically. All right, so it's a very nice remark. On the other hand, remark, while n this, how do you spell distinct? While n distinct eigen values is enough to show a matrix is diagonalizable, it's not needed. You don't always have to have n distinct eigenvalues to show that a matrix is diagonalizable. It is not required. So what I'm trying to say is if you show your matrix has n distinct eigenvalues, if you show a 5 by 5 has 5 distinct eigenvalues, then you automatically know it's diagonalizable. But just because a matrix is not diagonalizable means that it has to have distinct eigenvalues. Indeed, remember our example that we saw previously? 2, 2, 1, 1, 0, 0, 1, negative 1, and 0. This matrix that we saw just a little bit ago, yeah, at the beginning of class. This right here didn't have distinct eigenvalues. This had lambda is equal to, let me remember. This had lambda is equal to 1 with multiplicity 1, and lambda is equal to 2 with multiplicity 2. Okay? And this was diagonalizable. That is to say, low on battery. So that is to say, even though I don't have distinct eigenvalues, that is to say, I have 3 eigenvalues, but they're not all distinct. One of them is kind of repeated. That I'm still able to argue that this thing is diagonalizable. Okay. So kind of to summarize it, if you want, if you're able to show a matrix has distinct eigenvalues, then you can just say by a theorem from class it has to be diagonalizable. So if you're able to show a matrix has distinct eigenvalues, you're able to just say it's diagonalizable. But just because it's not having distinct eigenvalues does not mean you can automatically conclude that it's not diagonalizable. You may still have diagonalizability in that case. Yeah. Okay. So I think I have one more theorem. Um, one more theorem that's kind of technical, but you know, kind of look at what the examples that we've been seeing are. The examples that we've been seeing have been kind of enough for kind of the situations that we're looking at in this class. And this theorem is just trying to summarize all the possibilities in concise language. But because the language is so concise, it kind of obscures some of what's happening here. Okay, so let A be inside of Rnn, whose distinct distinct eigenvalues are lambda I, where I goes from 1 up to however many distinct eigenvalues you have. Of course, the maximum number of distinct eigenvalues you can have is going to be n. All right, and so kind of just so you have in your mind an example of this, I want you guys to kind of think about, maybe I'll write it here, think about this this example right here. I'll just write it all again. It's kind of fine, I think. So this one that I just wrote above us here, right? This had lambda was equal to 1 with multiplicity 1. And this the eigenspace, the null space of A minus I was given by the span of 0, -1, 1. This was our previous example. That's bullet point number 1 maybe. And bullet point number 2 is that lambda was equal to 2 was the other eigenvalue, and it had multiplicity 2. And the null space, the eigenspace of this was the span of, I don't have enough room, so maybe I'll write it here, was the span of two vectors, 1, 0, 0, and -1, 0, 1. All right. So for this example, what does this theorem look like? The number of distinct eigenvalues is p is equal to 2. All right, so in this case, there's 2 distinct eigenvalues, even though n was equal to 3. One of the distinct eigenvalues was 1, and the other distinct eigenvalue was 2. Okay, so that's kind of what this theorem is saying. Grab the distinct eigenvalues and just give them a label. So we're kind of writing them down without multiplicity. Then part A of the theorem says the following. For each one of these values, for 1 less than or equal to k less than or equal to p, the dimension of the eigenspace for lambda was equal to, for lambda k, I should say, for lambda k is less than or equal to their multiplicity, the multiplicity. All right, so for this example here on the right that we kind of looked at previously, for lambda is equal to 1, the dimension of the eigenspace was 1, and 1 is definitely less than or equal to 1. And then for this one, for lambda is equal to 2, the dimension of the eigenspace was 2, and that corresponds to the multiplicity. All right, but there was our non-example where the eigenspace had where the eigenvalue had multiplicity 2, but the eigenspace only had dimension 1. Okay, so part B is A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equals n. So in this case, on the right here, the eigenspace here had dimension 1. The eigenspace here had dimension 2. 2 plus 1 is 3, which is exactly the size of the matrix that we were looking at. All right? So that's what this is kind of trying to say. And then last but not least, part C is saying the sum of the eigenspaces equals n if and only if two things happen. One, the characteristic polynomial factors into linear factors. So the characteristic polynomial factors into linear factors. That is to say, you end up with distinct eigenvalues. That's all that this means. You end up with distinct eigenvalues, is what this is trying to say. And so we know that. We know that if I end up with distinct eigenvalues, then I end up with a diagonalizable matrix. All right. And two, or I should say, or two, the dimension of the eigenspace for each lambda k equals the multiplicity of lambda k. All right, which is kind of what happened in our second example that was diagonalized with in this example, I should say. Right, so we know that if I had distinct eigenvalues, I'm good to go. So this right here, what in the world is this saying? It's saying this part above. Here I have one of my eigenvalues, and here I have, here I have one of my eigenvalues, and here I have another one of my eigenvalues. Lambda is equal to 1 and lambda is equal to 2. When the dimension of the eigenspace, which is 1, matches the multiplicity, which is 1, then I'm happy. Here, same thing happens. The dimension of the eigenspace, which is 2, equals the multiplicity of lambda is equal to 2, which is 2. All right, and so whenever I have enough, kind of the way you can summarize this if you want, whenever I have enough eigenvectors, then I'm happy and I'm good to go. Okay? So kind of a way of kind of, seeing this result, if you want, through, let's say, through an example, if you want. Do I want to give you, I think I want to give you a new one here. Sorry, I'm looking up the example. Oh, okay. So, well, maybe there's a homework problem. So suppose A is a 5 by 5 matrix with eigenvalues. Lambda is equal to, let's say, pi with multiplicity 2, 1 with multiplicity 1, and then E with multiplicity 2. All right, so it's a 5 by 5 matrix, and I'm saying pretend it has 5 eigenvalues. 2 of them are pi, one of them is E, one of them is 1, and then 2 of them are E. Okay, so that's what this is saying. All right, and now I'm going to suppose that the null space of A minus pi I is, and I'll kind of write them all down all at once. Is two-dimensional, one-dimensional, and one-dimensional. Is A diagonalizable? All right, this is meant to be an example for this last point here that you're not being able to see. The dimension of the eigenspaces of lambda k equals the multiplicity of lambda k. All right, well, what is the dimension of the eigenspace for this guy? It's 2. What is the multiplicity? 2. So we're good to go. So that one checks out. What about here? What's the dimension of the eigenspace? It's 1. Well, what's the multiplicity? 1. Last but not least, the dimension of this guy right here is 1, but what's the multiplicity? 2. So I don't have enough eigenvectors, enough linearly independent eigenvectors to get a basis here. So I can see just by counting, without knowing what A is, just by counting, the fact that the dimension, right, that's what this is trying to say. The dimension of the eigenspaces, in this case, is going to be 2 plus 1 plus 1, which is 4, does not equal the sum of the multiplicities, which is 2 plus 1 plus 1, which is 5. So this is not going to be diagonalizable. So solution, since the dimension of the eigenspaces equals, well, for pi, it's going to be 2. For 1, it's going to be 1. And then for e, it's going to be 1. This equals 4. And the dimension, and the sum of multiple, not the dimension, sorry. How did I write it here? But the number of eigenvalues equals 5, then A cannot be diagonalizable. So that is to say, this is what it means to not have enough eigenvalues. To be honest with you, all you have to do is write down this line right here. You just have to say that for this particular, who cares about the other ones? Maybe it works for the other ones, maybe it doesn't. But because for this one it doesn't work, I get to be done. The dimension of the eigenspace is 1, but the multiplicity is equal to 2. So it can't be diagonalizable. All right. And armed with that, I'm going to finish off with one last example. It'll be kind of a, let's say, a quick one, just so you guys are able to kind of digest everything. So example, let A be 1, -2, 1, 0, 1, 3, -2, -1, and then -1. Diagonalize A if possible. All right, so I won't do all of the steps for us this time, but maybe I'll write down what you need to do in order to do the steps. So solution, if you want. So step 1 is find what? The eigenvalues. Whenever you see the word, how do you spell eigenvalues? Whenever you see the word diagonalize, it means you have to find all of the eigen stuff, all of the relevant eigen stuff. That's what this is saying. Okay? And so when you do this, how do you do this? You have to compute the determinant of a minus lambda I, that's the characteristic polynomial, and set it equal to 0. All right, so I won't do this for us if that's okay with you guys. But maybe I'll tell you guys what you get, and then you guys can kind of if you want, you guys can kind of verify this yourselves. All right? Yeah. So in this case, you're going to end up with some characteristic polynomial, and the solution of the characteristic polynomial tell you that lambda is equal to 0, has multiplicity 1, and 2 has multiplicity 2. All right, so you end up with 3 eigenvalues for this 3 by 3 matrix. And armed with the eigenvalues, you can do step 2. Find, so I'm kind of doing this quickly just so you guys can kind of get a roadmap of this. Find the eigenvectors of A. All right, so you have to grab the first eigenvalue, which was apparently lambda is equal to 0. Right, what does this mean? It means you have to compute the null space of A minus 0I. And then when you kind of do this, when you kind of do the work of this, you're going to see that the null space of A minus 0I is just going to be the span of 1, 1, 1, which is one-dimensional. So in particular, the multiplicity of lambda equals 0 is 1. The multiplicity of lambda is equal to 0 is 1. And the dimension of the eigenspace is 1. So they equal, and so there's a chance that this is diagonalizable. Lambda is equal to 2 is the real hard one. That's where the real money is. In this case, I have multiplicity 2. And so I need to pray that this eigenspace right here has 2 linearly independent vectors. All right, and if it does, then we have a chance to be invertible. All right, so I have to compute the null space of A minus 2 I. And as before, when you do this, when you're going to show that a minus 2i, I guess, is given by the span of the vector negative 2, 1, 0, 1, 0, 1. And this is going to be dimension is equal to 2, which is dimension 2. All right, and so now I notice that the sum of the dimensions of the eigenspaces, 1 and 2, gives me the size of the matrix, which is 3. Okay, so since the sum of the eigenspaces, which is 1 plus 2, which equals 3, equals the size of A, right? It's a size equals 3. What do we know? Then A is diagonalizable. Okay. All right, and now I can diagonalize it by, constructing P, constructing D. So maybe D is probably easier to construct. Let me start off with D. So it's going to be the matrix of eigenvalues. It's going to be 0, 2, and 2, and then zeros everywhere else, right? This right here corresponds to the eigenvalues. I have eigenvalue 0 with multiplicity 1, and then I have eigenvalue 2 with multiplicity 2. Okay? And now what is P? P is going to be the eigenvectors corresponding to these eigenvalues. Well, which were the eigenvectors corresponding to lambda is equal to 0? The vector 1, 1, 1. Vector 1, 1, 1. And then similarly for the other ones, it's what we get over here, negative 2, 1, 0, 1, 0, 1. All right, and so as usual, you kind of have to check that the P is invertible. So note, this is the part that people forget to do. The determinant of P is equal to just 1, 1, 1, 1, 0, negative 2, 1, 0, 1. I can probably get away with do I want to do a single row operation to get an extra 0? I think I will. What I'll do is I'm going to grab row 3 and I'm going to replace it with row 3 minus row 1. So that means nothing happened over here. Nothing happened over here. And then over here, I will just subtract 0, 2, and then 0. All right. And I did this because now I end up with an entire column of zeros. With a column that has 2 zeros, I should say, not an entire column. All right. It's going to be plus, minus, plus. Good. All right. So this is going to be plus 1 times this kind of subminor here, 1, 1, 0, 2. This is a triangular matrix, so it's going to be 1 times 2, which is just 2, which notably is different than 0. So P is invertible. This is why A is diagonalizable. Okay. I hope that helped. This was, I gave you guys, I think maybe like 4 or 5 examples of diagonalization. This video ended up being a little bit longer than I thought, but the good news is you guys aren't going to have to be, watching this in person with me or anything like that, or we don't have to do this in person or anything like that. I'll just post it and you guys can kind of watch it at your leisure. And then I look forward to seeing everybody on Friday, May 8th. Okay, so I'll go ahead and stop the screen share. And I'll stop the recording and I'll say thanks so much for everyone's time and attention. You guys have a good rest of your day and take care.